So today we will start continuous time Fourier series. So as you may remember from previous weeks, we have seen that we can represent signals as a linear combination of shifted impulses. So it was easier to visualize in discrete case. So we have just scaled and shifted impulses and summed them to obtain an arbitrary signal. But in continuous case, it was somehow tricky. So we have used staircase approximations and some integrals. Well, today we will continue with this motivation. We will see that we can write signals, periodic signals, especially actually, as linear combination of some basic signals. So those basic signals are actually nothing but complex exponentials. So if we have some periodic continuous time signals, we will see that we can find a Fourier series representation, and this representation expresses those periodic signals as linear combinations of complex exponentials. So this is the topic of this chapter. In the next chapter, we will see that regardless of their periodicity, we can write continuous time signals as some combinations of exponentials, again some simple signals, and the following sections, following chapters will continue with those properties of discrete time signals. So this chapter and next chapter is devoted to continuous time signals, and the following two chapters are devoted to discrete time signals. So first, we will start with analyzing response of an LTI system to complex exponentials. If I have a basic signal, let's say I have a k of t. So this ak is a very basic signal. Let's say we will define its properties later on. And if this is input to some LTI systems, and at the output, let's say we have bk of t, and this bk of t, we want this to be an easy to calculate signal. So this must be easy to calculate, let's say. So I will find some ak, which is a basic signal, and when this ak is input to an LTI system, then I will have bk, and this bk is a fairly easy signal to calculate. Then, so I will try to find such an ak, by the way. Then, let's assume that I have some linear combinations of this ak of t. So if this is input to my LTI system, at the output, I require to have, again, linear combination of this bkt. So this is what I need to have. So what is this ak? So I will try to find this simple ak of t. Well, it turns out that actually both of those properties, so property 1 and property 2, are satisfied by complex exponential signals. So if you have e to the power st in continuous time, and if you have z to the power n in discrete time, actually these signals are satisfying those two properties. I can find outputs easily. I can represent input signals as linear combinations of those very, very basic signals. So if I have an LTI system, let's try to understand the effect of e to the power st for this LTI system. So I want to find the output y of t if I have e to the power st as the input. So since system is time invariant, due to time invariance, I know that if I shift the input, I know by heart that the output is also shifted. This is due to time invariance. So what goes, I know that e to the power st times e to the power s tau. So I can separate this term, which is e to the power st times e to the power s tau. And I know that this is, at the output, I have actually y of t plus tau. So this is due to time invariance. So what about linearity? Due to linearity, I know that e to the power s tau and y of t is equal to, so I note that the variable is with respect to t, so e to the power s tau is a constant, so this is constant. So I'm multiplying the input by e to the power s tau. So if I multiply the input by e to the power s tau, due to linearity, the output is also multiplied by e to the power s tau, and I know that this is equal to y of t plus tau. So due to linearity and time invariance, I know that e to the power s tau times y of t is simply equal to y of t plus tau. So if t equals 0, then I have y of tau is equal to y0 times e to the power s tau. I can change tau to t. It does not depend. It does not matter. So this tells me that actually if tau equals t, y of t is equal to y0 times e to the power st. So it is easy. It tells me that if you have e to the power st at the input, the output simply y0 times e to the power st. So that's quite easy. So I have shown that actually this e to the power st satisfies at least the first property. So if it is input to an LTI system, the output is simply the signal e to the power st times a scalar. So this is quite easy to calculate. So this is one of the main motivations that we will use e to the power st to represent continuous time signals. So to let's say emphasize once more, if I have an LTI system here, the output is simply y0 times e to the power st. So this is the case. Well, at this point, we can define eigenfunction of an LTI system. In general, an eigenfunction of a system is a function such that the response of the system to such a signal is itself multiplied by a constant. So you have a signal at the input or a function at the input. At the output, you have the signal multiplied by a scalar. So if I have, in general, if I have phi k of t, and if it's input to any system, then at the output, let's say I have lambda k times psi k of t. So this is so-called eigenvalue, and this is called as eigenfunction. So what does it tell you? If phi k of t, psi k of t, let's say, is eigenfunction of a system, the output is this eigenfunction multiplied by a scalar, and the scalar is nothing but its eigenvalue. So what about our LTI systems? For LTI systems, actually complex exponential signals are eigenfunctions. So what does it tell you? Let's again write a general LTI system. I have it is simply yt is xt convolved with h of t. So let's select x of t as e to the power st. Then what's the output? Y of t is integral from minus infinity plus infinity h of tau x of t minus tau d tau. It is equal to integral from minus infinity plus infinity h of tau e to the power st minus tau d tau. So this is simply equal to, actually this integration is with respect to tau. So I have e to the power st is constant with respect to tau, so I can take it out, e to the power st times integral from minus infinity plus infinity h of tau e to the power minus tau d tau. So if you have e to the power st at the input, at the output you have e to the power st times something. So the something is actually the eigenvalue. So this is the eigenvalue, and this e to the power st is the eigenfunction. Okay, so complex exponentials are nothing but eigenfunctions to LTI systems. So in general, what do you have? If in general you have such an x of t, so in general I have this x of t, it is summation k from minus infinity to plus infinity a k e to the power skt. If this is input to an LTI system, at the output I have nothing but y of t, which is equal to, again, summation k from infinity to plus infinity a k h of sk e to the power skt. So this is the response of your LTI system to a signal x of t, which is a linear combination of complex exponentials. So we will have more on this h of sk. Actually, it is defined above here, but we will, have more examples on that. So let's start with a very simple example. I have a system which is output relationship is defined by y of t is equal to x of t minus 3. So the first question is the system LTI? If so, determine first its impulse response. So remember, we have impulse responses defined only for LTI systems. So if you have an LTI system and the output is nothing but h of t. So if you have an LTI system, then you have its impulse response. And for impulse response, you have impulse of t at the input, and at the output, you have h of t. So it tells us to determine its impulse response. If it is LTI, then determine the output of the system to inputs x1 and x2. So first, please note that, of course, the system is LTI, and it is a pure delay system. So the system is a pure delay system. So it is LTI, of course. So this is our first question, first answer. The second part is determine its impulse response. So I know that if x of t is impulse, y of t is the impulse response. So h of t is simply impulse of t minus 3. So that's it. In the third part, I will find the outputs for x1. So I know that y1 of t is simply x1 of t convolved with h of t. It is equal to e to the power 2jt convolved with impulse t minus 3. Well, I know that you can tell this by heart. So if you convolve a signal by a shifted impulse, you have nothing but you replace t by t minus 3, and I have e to the power minus j6 times e to the power j2t. So this is the first way, so an easiest way. I have actually used the shifting property. Remember shifting property. And by using shifting property, I have calculated the output. So let's try to use this h of s stuff. So if you try to find h of s, it is simply integral minus infinity to plus infinity, impulse of tau minus 3, e to the power minus s tau, d tau. So again, by using shifting property, it is e to the power minus 3s. So this is my h of s. I know that y of t is h of s times e to the power st. So I know that y of t is simply h of s evaluated at s equals j2 times e to the power j2t. So instead of s, I have now j2. So that's it. So I have evaluated h of s at s equals j2, and it is simply e to the power minus j6 times e to the power j2t. So in both cases, I have the same result. So the upper one is the direct convolution, and by using this direct convolution, I use the shifting property. And in the second one, I used this eigenfunction and eigenvalue property in previous page. So I have found h of s, and h of s is simple since I have an impulse. Again, by using shifting property, I have obtained h of s. So to find the output for e to the power st, s being equal to j2, I have simply put s equals j2 in h of s relation, and use that this is the eigenfunction, this is the eigenvalue, and obtain the output as before. So what about the second case? What about y2? So y2 is actually x of t convolved with h of t is equal to, I know that again by using this direct shifting property, I will put t equals t minus 3 to find the output easily. So it is cosine 4t minus 12 plus cosine 7t minus 21. So this is direct way. And in the second way, I will use the eigenfunction and eigenvalue property. To do this, first I will write cosine 40 and cosine 70 in terms of complex exponentials. So I know that cosine 40 is nothing but 1 over 2 e to the power j 4t plus e to the power minus j 4t. And I know that cosine 70 is simply, again, 1 over 2 e to the power j 7t plus e to the power minus j 7t. So these are actually my inputs. So input is a linear combination of e to the power j 40, e to the power minus j 40, e to the power j 70, and e to the power minus j 70. So my input is a linear combination of those signals. So what I know, let's continue from top. I know that the output is also linear combination of those inputs, but with scaled versions. Okay, so I know that my y2 of t is simply 1 over 2 8j4 e to the power j 4t plus 1 over 2 h minus j4 e to the power minus j 4t plus 1 over 2 h j7 e to the power j 7t, and finally 1 over 2 h minus j7 e to the power minus j 7t. So this is my final output, and I know that h of s is nothing but e to the power minus 3s. To find, let's say, h of j4, it is simply e to the power minus 3 times j4. So it is e to the power minus 12j. So if you put everything in place as the homework at your home, try to evaluate this form and see that it is equal to this y2 relationship. If you rearrange terms, you will find that those two relations are equal. Okay, so this is again a motivation to make you familiar with complex exponentials and if they are input to let's say LTI systems. Well, then comes the Fourier series. Fourier series actually based on the fact that I can find linear combinations of harmonically related components and represent my periodic continuous time signal with linear combinations of harmonically related exponentials. So first, remember a periodic continuous time signals, if it satisfies this property, t is the period. Okay, so this is how we define the period and periodicity. And again, remember that the fundamental period t0 is actually nothing but minimum positive period t. So remember that if a signal is periodic with t, it is also periodic with integer multiples of t. So smallest of those periods, of course, which is positive, is your fundamental period. Then again, the fundamental frequency omega 0 is, remember, defined as 2 pi over t0, and it is equal to 2 pi f0. So this is the fundamental frequency. Then, for example, two basic periodic continuous time signals, which are periodic with omega 0, or let's say cosine omega 0 t and e to the power j omega 0 t, are all periodic with t0, and omega 0 is their fundamental frequency. So now let's consider the idea of harmonically related complex exponentials. Well, if I define this phi k as e to the power j k omega 0 t, then actually these are harmonically related. All of has the common period, but the fundamental frequency and the fundamental period of the kth component are as this respectively. So this is k omega 0. This is nothing but 2 pi over k omega 0. So remember, period is positive, so it's non-negative and non-zero. So I put it here absolute k omega 0 because k can be plus minus. So for phi k t, I have, this is its fundamental frequency, and this is its fundamental period. So if k equals 1, I have the uppercase. So for k equals 1, I have the below discussion. But if k is not 1, it is in general a number, then this phi k has the fundamental frequency of k omega 0 and fundamental period of 2 pi over k omega 0. But all of those signals, all of those phi k's are actually having the same common period. Remember, any multiple of the period is again the period of the signal, right? Remember, so if I multiply this with k, then it does not change. This 2 pi over omega 0 is the period of this phi k. Not fundamental period, but the period. So if a signal is periodic with 2, it's also periodic with 4, it's also periodic with 6. So all of those phi k's are periodic with the common period, and which is 2 pi over, let's say, absolute omega 0. Again, omega 0 can be negative, so I put it here an absolute sign to make everything, let's say, safe. So this is called as T common. So 2 pi over omega 0 is the common period of all of those phi k's. So 2 pi over omega 0 is not the fundamental period for all of them. It is only fundamental period for the first component with k equals 1. So it is actually called as a fundamental component. But I know that multiplying the periods with some integers, the number that I obtain is again the period of the signal. So for all of those phi k's, 2 pi over omega 0 is the common period. So if I have a linear combination, xt, so if I have a linear combination, it turns out that this linear combination on xt is also periodic with the common period. Okay, so it is equal to 2 pi over absolute omega 0. So this is the common period. So at this point, let's introduce the Fourier series representation for continuous time signals. So if you have xt, you can represent it as linear combination of harmonically related complex exponentials. So a representation of this form is called as the Fourier series representation of periodic signals. And this periodic signal x of t has this period 2 pi over omega 0, Again, we assume that omega 0 is a positive number, so T0 is. The coefficients AK are called as the Fourier series coefficients, or they are called as the spectral coefficients. So those AKs are the Fourier series coefficients. The fundamental component of Fourier series representation is the terms with k equals plus minus 1. So the terms with k equals plus minus 1 are the fundamental components. What else? The nth component or nth harmonic component of this Fourier series representation is simply the terms with k equals plus minus n, and the DC component is the term with k equals 0. So the term with k equals 0 is the DC component. It is actually the unique term. Well, here I have some remarks. Note that we did not show that any continuous time periodic signal can be written in the form above. So the signal should satisfy rules that we will go over in section 3.4. But we shown that if a periodic continuous time signal can be written in the above form, by the above form I mean that this form, if it is written in this form, then it is periodic with T0, and this representation is called as the Fourier series expansion. We will see that signal must satisfy some properties to be written in the form of Fourier series, but actually most of the signals that we use, that we encounter in engineering, are actually represented can be represented with Fourier series representation. So here I have an example. Consider x of t written in this form, and I have a0, a1, and the coefficients are given. So what is x of t? So let's write x of t. It is 1/3. So I'm only evaluating this, nothing more. So for k equals minus 3, I have a minus 3. For k minus 2, I have a minus 2. It is 1/2. For k minus 1, I have 1/4, and it goes on like this. So I will start with writing a minus 3 times e to the power minus 3 times 2 pi t. So I will start with writing the first term. It is 1/3 e to the power minus j6 pi t plus 1/2 e to the power minus j4 pi t plus 1/4 e to the power minus j2 pi t plus 1 times e to the power 0 plus 1/4 e to the power minus j2 pi t plus 1/2 e to the power j4 pi t plus 1/3 e to the power j6 pi t. So I have those terms. Now I will rearrange them. First, I have the DC term in 1/4 parentheses j2 pi t plus minus j2 pi t plus 1/2 j4 pi t and it's equal to 1 plus 1/2 cosine 2 pi t plus cosine 4 pi t plus 2/3 cosine 6 pi t. So this is my x of t. I use the Euler's relation to convert complex exponential sums to cosines, and that's it. So if you go and check, so this is the DC term with k equals 0. This is the term with k equals 1. So if you sum those two, you have this term. So this is the term with k equals 2. So if you sum those, let's say, three terms, this one, and this one. This is what you have. So as the terms are added up, actually, step by step, you can see the construction of x of t. So it is this weird signal in the end that are obtained by combining those signals. But actually, you see that although it is weird, it is periodic. So since it is periodic, I can write it as in the form of Fourier series representation. So in general, what if you have a continuous time periodic signal and if you want to find AK coefficients? So actually, we have two methods. The first one is the coefficient matching approach. So this coefficient matching approach depends on just some inspection. So if we have x of t as an example, which is equal to sine omega 0 t, I will first write x of t as in this form. It is 1 over j2 and e to the power j omega 0 t minus e to the power minus j omega 0 t. So this is my x of t signal. And from this, I know that a1 is simply 1 over 2j. A minus 1 is minus 1 over 2j. And ak equals 0 for k not equal to plus minus 1. So this is my coefficients. Ak is 0 if k is not equal to plus minus 1. A1 is 1 over 2j. A minus 1 is minus 1 over 2j. And of course, the fundamental frequency is omega 0. And fundamental period is simply 2 pi over absolute omega 0. So if someone tells you that omega 0 is positive, then you can omit this absolute sign. Or as a more general example, let's assume I have this x of t given. So I will first write it in exponential form using Euler's relationship. It is 1 times e to the power 0 plus 1 over 2j e to the power j omega 0 t minus e to the power minus j omega 0 t, okay, plus, let's continue from there, or let's go here, plus e to the power j omega 0 t plus e to the power minus j omega 0 t. So this is this cosine term, plus 1 over 2 e to the power j 2 omega 0 t times e to the power j pi over 4 plus e to the power minus j 2 omega 0 t times e to the power minus j pi over 4. So this is my x of t. Then by just looking at the terms, I can tell you that a0 is nothing but 1, a minus 1 is nothing but 1 minus 1 over 2j. So a plus 1 is 1 plus 1 over 2j. A minus 2 is simply 1 over 2 e to the power minus j pi over 4. A plus 2 is the positive term, e to the power j pi over 4. And ak is 0 else. So for the rest, I have ak is 0. Again, the fundamental frequency is omega 0, and the fundamental period is 2 pi over absolute omega 0. So I obtain the terms from a minus 2 up to a plus 2, and the rest are equal to 0. So as a general approach, how can I find the coefficients ak? So I'll tell you that actually this is the way to obtain ak. So 1 over t0 integral from 0 to t 0 again in one period. X of t to the power minus j omega 0 t is the way to obtain the ak coefficient. So you can put here t0 actually. So over one period. So x of t is actually, if it's periodic, all using the fundamental period. So How to prove this? So first, let's start with writing x of t. So this is the general form, and AKs are Fourier series coefficients. I multiply both sides with this e to the power minus j n omega 0 t and integrate. So I multiply both sides with e to the power minus j n omega 0 t and integrate. So what is it? Integral from 0 to t0 x of t e to the power minus j n omega 0 t dt. So this is equal to integral from 0 to t0. I will put this summation term instead of x of t, summation k from minus infinity to plus infinity, a k e to the power j k omega 0 t times e to the power minus j n omega 0 t dt. So I will, as usual, switch integrals and summations. Let's continue here. It is summation k from minus infinity to plus infinity, a k, an integral from 0 to t0, e to the power j k minus n omega 0 t dt. Well, let's put here a term. So I cannot put this term out because there is this k here and there is this k here. So actually, this is an interesting term. So the result is simply t0 if k equals n. So if k equals n, I have e to the power 0, which is equal to 1, and integral from 0 to t0, 1 dt is simply t0. So if k equals n, this integration is t0. Well, otherwise, it's equal to 0. Why is this so? So please note that there's a signal e to the power j something omega 0 t. And this e to the power j something omega 0 t is integrated over one period. So I know that actually this something is a scalar with respect to t. And if I multiply omega 0 by something, it means that I'm increasing the frequency, decreasing the period. But whatever this number is, the signal e to the power j something omega 0 t is periodic with t0. So the fundamental period is actually 2 pi over something times omega 0, but the period is t0 is a period. So I am integrating it over a period. So if we integrate a sine or a cosine or a periodic exponential or a sinusoid over a period, the result is nothing but 0. So it is 0 due to the integration of a complex exponential over whole period. Okay, this is the case. So this is equal to nothing but summation, again, k from minus infinity to plus infinity, a k times t0 times impulse k minus n. So what does it tell you? This impulse k minus 1 is actually telling you that this is equal to 1 if k equals n, 0 otherwise. Okay. So this summation is with respect to k. Again, using the shifting property, I will put k equals n. So this is t0 times a n. So that's it. So this integration is nothing but t0 times a n. So what was this integration? Remember, it was integral from 0 to t0 xt e to the power j n omega 0 t. So finally, I have a n is equal to 1 over t0 integral from 0 to t0 x of t e to the power minus j n omega 0 t dt. So put k equals n and obtain this relation. Okay. So I have written for n, but actually You can put k equals n if you wish. Nothing changes. It's an auxiliary variable. Just like this, I can put here tau, I can put here tau, I can put here tau, nothing changes. I can put here k, I can put here k, nothing changes. So these are auxiliary variables. Well, the proof is actually not so much hard. Now I have at this point the synthesis and analysis equations. So this is the so-called synthesis equation. This is so-called the analysis equation. So what does those equations tell you? Well, by the way, this interesting sign tells you that the integration is over one period. So it can be from 0 to 0, from any t0 to t0 plus t0. So the integration length, actually, the limits, when you subtract the limits, the integration length is t0, or from 2 to 2 plus t0, so whatever 2 is. So actually, this tells us that actually this t0 is just the integration period. This synthesis analysis equation are telling you that if somehow you have a period signal xt, and if somehow you can, if you calculate the AKs, given AKs, you can calculate xt. Given xt, you can calculate AK. So these both are, let's say, representing the same signal. Given xt, you can find AK. So AK uniquely represents your signal xt. So if someone gives you AK, you can reconstruct the original signal xt, or if you have xt, you can find AK. So both representations, both actually xt and AK are giving you the same signal. So it's an alternative way to represent your xt using AKs. I have a periodic square wave. I will not actually go over this example, but it's quite easy. I will solve it next week. Sorry, not next week, but the following week. So please, for the next lecture, please come with those concepts reviewed. So the concepts are not so much hard, but I know the mathematics is somehow new to you, but it is, believe me, easy. So just some basic calculus that we are using. So please, when you come next time, review this continuous time Fourier series. So this is all for today for me. Actually, let me stop recording.